This is the one-dimensional kinematics topic. This section is calculating distance versus displacement with some problems that are a little more difficult than just running east, running west, running north, and running south. We're going to be going all over the place and then trying to look for triangles and other geometric figures so that we can figure out the displacement, figure out a way to calculate the displacement. All right, here we go. I'm going to move a little bit more quickly because we introduced all the ways to calculate displacement in the earlier sections. All right, so we're going to move a little bit more quickly on these problems. Okay? All right. We've got a young man named Jim, and he wants to go 2 meters east, then 4 meters south, and then 5 meters west. All right, so let's see, 2 east, 4 south, 5 west. Let's start over here a little bit. All right, so we'll start Jim right here. All right, start. And he wants to go 2 meters east. So I'm going to go 2 decimeters east. Okay, 2 decimeters east. Label it with the actual parameter, 2 meters east. All right, then he wants to go 4 meters south. All right, where's my 2 ending? Oops, that's inches. All right, 2. All right, we're right about there. Now 4 south. Okay, I'm going to fit that there. All right, 1, 2, 3, 4 south. Okay, and then 5 meters west. Okay, so put that there and go 5 meters west. Okay, so there's Jim ends up over here. There's the end. Now, note 2 meters east, 4 meters south, and 5 meters west. Tip to tail, all right? Tip, tail, tip, tail, tip. Okay? Now, we get our displacement. The resultant is straight from start to end. So we'll put our resultant right there. Straight from start to end. Jim went that way. Put the arrow. That's our resultant. All right, or Jim's ultimate displacement. Okay, now let's add up the distance that Jim covered first. All right, the distance total would be D1 plus D2 plus D3. D1 was 2.0 meters, D2 4.0 meters, and D3 5.0 meters. The total distance that Jim covered, all right, is 11 meters. All right, the total distance that Jim covered was 11.0 meters. All right, now let's try to figure out his displacement. The key to figuring out the displacement is looking for triangles. In a lot of physics and math, the key to figuring out problems that are complicated is looking for triangles, looking for rectangles. All right, you need to be able to calculate that displacement right there, that resultant. All right, so do you see a triangle somewhere? I'm going to give you a minute to look for that triangle. All right, do you see a triangle? Okay, oh, you do. Okay, well, there's your triangle, right? If you drop a line, all right, an imaginary line right down there, all right, there's your triangle. See the triangle? All right, so now you've got a right triangle, okay, and you're going to be able to calculate that hypotenuse to get the displacement. All right, so now let's figure out, based upon the information that we do know, as many sides of this right triangle as we can. Now, if this is 4 meters, then this leg here must be 4 meters, right? So this is 4 meters, all right? And if this is 2, and the whole thing is 5, right? If this is 2 over here, this little section, right? And this whole thing from here to here is 5, then this section must be 3. So the triangle that we have here is a 3, 4, obviously 5 right triangle. But we're going to calculate this anyway because you're going to get some more complicated problems where it's not a 3, 4, 5 and you're not sure, so you're going to have to do Pythagorean Theorem. So let's do Pythagorean Theorem. I'm going to call this D, I'm going to call this A, and I'm going to call this leg B. All right, so D squared is going to be equal to A squared plus B squared. All right, A is 3.0 meters squared, B is 4.0 meters squared. We've got 9 plus 16, that's 25. So we're going to take the square root of 25. All right, and the displacement, the magnitude of his displacement, of Jim's displacement, is going to be 5.0 meters. All right, we've got the magnitude. Let's get the angle. Now, Jim didn't go west, he went near, right, south of west. You need this angle right here to describe Jim's direction, the direction of Jim's displacement. All right, what you really want is this angle. You want this angle right here. Well, that's going to be the same as this angle here, okay, from geometry, all right, alternate interior angles. All right, now, we want this angle, so we're going to do opposite, which is 4, over adjacent, which is 3, so we're going to do tangent, all right, opposite over adjacent. We know that the magnitude is 5.0 meters, all right, so the tan of theta is opposite over adjacent. Right, this is the angle. We want that angle, so we're going to get this angle. It's the same. The opposite is 4.0 meters. The adjacent is 3.0 meters. All right, so tan theta. Take your calculator, 4 divided by 3. All right, 1.333. All right, I don't want the tan of theta, I want theta, I have to get rid of tan. So I take the inverse tan, whatever you do to one side, you have to do to the other side. Take the inverse tan of both sides, tan and inverse tan cancel, and theta is the inverse tan of 1.333. If you take the inverse tan of 1.333, right, you're going to find that this is a 53-degree angle. So theta is 53 degrees. So take a minute, pause the video if you want to copy any of that. All right, pause the video now, okay, because we're moving on. All right. So the distance that Jim covered was 11.0 meters, but Jim's displacement was 5 meters, comma, 53 degrees. Now, he didn't go west, he went near, right, he went that way, south of west. 53 degrees south of west. Okay? There's just magnitude for the distance. For the displacement, you have a magnitude and a direction. If they asked for only the magnitude, the magnitude of Jim's displacement, the answer would be 5.0 meters. You would not have to calculate the angle. If they ask for his displacement, technically, you've got to calculate the magnitude and the direction. Remember, the convention for direction is to say either north or south of either east or west. That is a popular convention. North or south first of either east or west. Okay, we've got one more challenging problem. All right? So let's get on to the next problem. For this next problem, a young lady named Crystal is going to do some walking. She's going to start about here. All right, that's where she's going to start. I'll put a dot right in the center there. She's going to go 3 meters south. First, she's going to go 3 meters south. Here we go. 1, 2, 3. Okay. Crystal walks 3 meters south. Then she walks 2 meters west. All right, there's our, we'll do it this way. There's our 2 meters west. Go, Crystal, go. 2 meters west. Then she's going to walk 5 meters north. All right, 5 meters north. Here she goes. 1, 2, 3, 4, 5. All right. She went 5 meters north. All right, and then she went 4 meters west. 4 meters west. Here she goes. Okay. So, 4 meters west. All right. So we're trying to figure out what her distance was. Here's where she ended. What distance did she cover? And what was her displacement? All right, her distance, add it up. All right. Distance total, D1 plus D2 plus D3 plus D4. D1 was 3.0 meters. D2, 2.0 meters. D3, 5.0 meters. And D4, 4.0 meters. Add them all up. She's got 4, 9, 11, 14. All right, 5 plus 5 plus 4. Okay, she's got 14. So the total distance that Crystal covered was 14 meters. All right, now, her displacement, straight from start to end, her displacement is right there. Okay, her displacement, straight from start to end. Okay, so there's her displacement. Now, how are we going to do that? Do you see a triangle? Do you see rectangles? What do you see? All right, how are we going to draw this so we can figure out what her displacement is? Do you see a triangle? A lot of times in physics with diagrams, you're looking for triangles. Okay? See the triangle? I see a triangle. All right? So if that's the hypotenuse, you've got a triangle. All right? There's one leg. Okay? All right, and there's the other leg right there. Okay? Let's fix that. All right? So you see the triangle. All right, now let's figure out the lengths of the legs. All right? If this is 2 and this is 4, right? Then this leg right here, right, is 2 plus 4. This leg here is 6 meters, right? This 2 plus this 4, this leg here is 6 meters. So we got that leg. Now, this leg here is 3. This from here to here is 5. So how much is this little piece over here? If this is, the whole thing is 5, and this piece here is 3, then this piece up here is 2 meters. And this piece is the same length as this piece. So this is 2 meters over here. So we've got our triangle, we can do the hypotenuse, we can get the displacement. Okay? So, little bit of geometry, a little bit of trig, a little bit of drawing kind of neatly. All right? Here we go. You want this displacement right here. We're calculating the magnitude first. Okay, here we go. So we'll call this D. All right. Some people like to call the resultant R. Want to call it R? That's fine. We don't care. Arose by any other name, right? We'll call this one A. I need a better marker. All right. We'll call this one A. We'll call this one B. Okay, and our hypotenuse is the resultant or the displacement R. So, all right, R squared equals A squared plus B squared. All right, A is 2.0 meters squared. B is 6.0 meters squared. All right, so we've got 4 plus 36 is 40. So R squared, the resultant, squared is 40. Take the square root of both sides. The resultant, the displacement, all right, is 6.3 meters. All right, 6.3 meters. Now, the direction. The direction is not west, right? It's near, right? North of west. It's north of west. It's not west. You have to go north a little bit. You have to go north by this angle here. So we need to calculate that angle so we can describe how many degrees north of west our answer is. Okay, so let's get that angle right there. Okay? Here we go. Okay, this angle, all right? Tan theta equals opposite over adjacent. Tan of theta, the opposite is 2 meters. The adjacent is 6 meters. That means the tangent of theta is going to be 0.333, right, 1/3. Okay. So the inverse tan of 0.333 is, right, 18.4. All right, take the inverse tan of both sides. All right, theta is 18.4. Theta is the inverse tan of 0.333. Theta is 18.4 degrees. All right, so our final statement, the distance and displacement that Crystal covered. Do you want to copy that down? All right, pause it. Here we go. All right, so the distance that Crystal covered was 14 meters. Crystal's displacement, all right, was 6.3 meters. There's her magnitude. Her direction was 18.4 degrees, not west, but north of west. 18.4. If you start west and you go 18.4 degrees up, all right, I'm pivoting right here at the elbow, right there is the pivot point. All right, 18.4 degrees north, all right, of west. All right, that's magnitude only for the distance. For displacement, which is a vector, you give the magnitude and the direction. All right, in this case, the direction is defined by an angle. I will see you in the next section.